Welcome to my presentation. My presentation is Design and Performance Analysis of Microstructure Optical Fiber for Fiber to the Home Applications. Presented by Junaid Ahmed from Bangladesh, paper code 0468 ICN TET 2018. My contents: microstructured optical fiber necessity, introduction of FTTx applications, important definitions, literature review, proposed design and simulation result and discussions, conclusion and future work. Here we can see the comparison of data transferring speed of a optical fiber with a copper wire and the optical fiber. Here the applications of fiber is sensor, medical imaging, fiber to the home, networking, communication, optical components, display and illumination. Here we can see the Snell's law, critical angle and Brewster angle. Here the different mode and types of conventional fibers, that is step index fiber, graded index fiber and single mode fiber. Here the optical windows and optical bands. Here O, E, S, C, L and U bands, where generally we use short wavelengths, S band. Here the light guiding mechanism and the comparison of conventional optical fiber and PCF. For conventional optical fiber, two demerits, that low index contrast and narrow design space. We can overcome these problems through microstructure optical fiber, that is for single material fiber, high index contrast and wider design space. That consist major demerits such as confinement loss exist, fabrication challenge. Introduction of FTTS application, installation and use of optical fiber from a central point to individual space such as residences or offices. We need a bending necessity fiber. Applications of bending necessity fiber, that is house appliances, smaller outside planet cable, cabinets, etc. We can see the practical use of bending necessity fiber in house. For design, a sharp bend we need, that is sharp bend, wall mounted TP box. Necessity of FTTS applications in voice, telephone, broadband, etc. in videos, TV, CATV, remote monitoring and data, computer, CPU to peripherals, LAN, aircrafts, etc. For sensor, gyroscope, position sensor and temperature sensor. Bending insensitive fiber for FTTH, we need the bending loss under 0.15 decibel per meter in radius of 5 mm and effective mode area is about 80 micrometers square. Here the different definitions, the mode field area. Here E is the total electric field by solving eigenvalue problem. Here the bending loss. Here the details of bending loss. Here for transmitting we need an optical repeater, that is chromatic dispersion. Here we can see the signal dispersion process. Here waveguide dispersion and material dispersion. Here splice loss, when we connect or join two fiber, it exists a loss, that is splice loss. Here the equation of splice loss. Here equiangular spiral we have used. The region of using equiangular spiral, the number of arms can be changed, or number of air holes or diameter of air holes, angular increment and air hole radius can be changed. That gives us low bending loss, high non-linearity, flat dispersion and ability to optimize the performance. Here are the different references where they use different fiber. We have used equiangular spiral, and that is the previous work exists higher bending loss. Here we have The objective of our work, the bending loss will be lower than 0.5 decibel per meter, low splice loss, and mode field area is around 80 micrometer square. Here our proposed design, we have used equiangular spiral cladding octagonal and base material silica. Here the design equation, our schematic diagram of proposed design and mode field distribution, a light confinement in x-axis direction, and our mesh we have used finer. Here the bending loss versus wavelength curve. Bending loss increases with increasing the wavelength, and here increasing wavelength and bending radius causes greater mode field area or effective area in equiangular spiral. Here the when the fiber is bent, a propagational loss, that is bending loss, take place due to bend in optical fiber. Here we have see the splice loss versus wavelength. The splice loss increases with decreasing the bending radius. Here the material dispersion. Material dispersion increases with increasing the wavelength. Here we can see the straight fiber loss and bending fiber loss. Here we can see the few loss for straight fiber and huge loss for bend fiber. Here we can see a comparison of previous works or our proposed design. We can see different bending loss, mode field area, structure, and design equation. In reference one, we can see huge bending loss and mode field area is high, and they have used large mode area optical fiber, and same use in reference 2. And our proposed design. Now the performance of our can be improved, and our performance can be investigated for different aspect ratio. Our reference. Thank you for listening.